needs to come in later. But here's all the stuff this week. Here's the lesson for Unit 1, Lesson 1. You can click on that, and I'm not going to go through all this with you. This is for you to read and go back and refer to. It's got all the notes you need for there. And Lesson 2 is beneath it. Lesson 2 is set up right there, so you can go through that information. And then there's our assignments for this week. We got assignment 1 and we have assignment 2, and they're both on formative. So that's your 2 assignments this week. You will need to watch this video before you do lesson 2. This regression lines video tells you how to get those lines when you go to Desmos. You can also do regression lines with like a TI-84 if you have one. Go ahead and Google that up on how to do those regression lines, because I didn't make a video for that since everyone has access to Desmos. So I won't play that now. Kill it. And we may, if we have time, we may do this together while we're here. So, all right. So lessons 1 and 2 notes right here. Like I say, if you can print those out, it will save you time. But otherwise, you should have some pencil and paper. Hello, Cora. So you need some pencil and paper to take notes if you don't have a printer available to print those out. But I'm going to go ahead and get started with the lesson 1 handout. Like I said, we've got a lot to cover. I'd like to do this all in one class period and not have to meet multiple times per week. That is the goal for this class. We're going to pack a lot into our Monday meeting, so we don't have to meet on Wednesdays or Fridays of those weeks. So you still have those times to work as you choose. So, all right, let me go ahead and switch to my handout camera. And here is our first handout that we're looking at. All right, so we are going to compare 3 different types of graphs. And this is kind of pulling back information from past classes just to get us started on there. First, I want to talk about linear. Linear. So if something's linear, what does the equation look like for linear? Y equals M. Oh, you're on top of it already. So mx plus b. And this is in function notation. That's the same thing as y equals. Same thing. It's just f of x equals mx plus b. So some examples of that. We can have y equals 4x minus 1. Other examples of linear equations. Doesn't necessarily have to be in the y equals. It could be 2x plus 3y equals 5. That's also a linear equation. Now we can rewrite that as y equals. All we have to do is solve that for y. But that's the same type of thing. So this is in standard form. This is in slope-intercept form. There's also like y minus 1 equals 2/3 parentheses x plus 2. That's in point slope notation. So linear equations can take different forms, but still you're just going to have an x right now. All right, so what are some of the characteristics, things that tell us it's a linear equation? Any thoughts on that? Characteristics of linear. Straight line, constant rate of change, like it. So when we graph it, it's a straight line. I'm getting Amber alerts on my phone here. It's going crazy here. From West Memphis. That's a long ways away from Amber. Yes, constant rate of change. Constant rate of change. It's a straight line when we graph it. X is our input, right? We input an X, and the Y is the output, right? And the Y, same thing as f of x, right? We can call it Y or we can call it f of x. All right, wonderful. Could be increasing or decreasing or constant, right? Increasing, decreasing, or constant. Or could have No slope whatsoever if it's straight up and down, right? Let's see. So let's make a table of something that would be linear. So we'll do like -2, -1, 0, 1, 2. Well, we got extra spaces here, 3, 4. So if we start at -10, go -5, the thing we're going to see is, this is a +5 each time. It's constant. Every time we see +5. So this would be 0, 5, 10, 15, 20. Right? Because with a constant rate of change, we see this rate of change. Every time x changes 1, y goes +5. So +1 and +5 every time on that. And let's see if we graph this particular equation, goes through 0, 0, goes to the point 1, 5, 1, 2, 3, 4, 5, 2, 10. So we graph this line like this. So that is the graph, an increasing graph, right? As we go right, it goes up. So that's a nice look at linear as a reminder. So let's change now, instead of linear, set that aside. Let's look at quadratic. Okay, so an equation for quadratic, what would that look like? X squared, right? And if you go for the full definition, it's ax squared, because a could be whatever the coefficient is. You could have a bx plus c, a squared plus bx plus c. If b and c are 0, it's just whatever the coefficient of the x squared is. So an example of that, of course, y equals, we can give it the coefficient values, 3x squared minus 6x plus 5. That's an example of a quadratic equation. We could also see it in factored form, right? Maybe you got x minus 2 times x plus 3 equals 0. That's also a quadratic equation, because when we multiply those two factors together, we'll end up with an x squared. So we know that that is also factored. We could see it as x minus 7 squared equals 0. Again, a quadratic equation. So what are some of the definitions or characteristics of what we expect to see with a quadratic? What do we see with a quadratic? A U shape, up of positive, down to negative. It's a parabola. All right, thank you for that. It has exponentials of 2. Okay, so U shape. So positive, if it has a positive, this, if it's a negative, goes down. I guess I should put little arrows on the end of that. Positive goes up, negative goes down. Exponentials of 2. So it means basically it has to have a square, ax squared. So we have to have that square in there for it to be a quadratic. Would highlight that. And mention the word vertex in there. So the vertex is just the highest or lowest point, right? Don't confuse the positive negative with the vertex. The vertex could be a negative vertex. It could be below the x-axis. Could have a vertex down here in the negatives. But if the parabola, if the x squared is positive, that's what's going to make it going to point up. If the x squared has a negative coefficient, it's going to point down. But the vertex could still be up here in the positive area. So don't confuse that. Let's see. So a table for our parabola. Let's go ahead and do the same numbers. 0, 1, 2. 3, 4. And let's say that our numbers over here are going to be 5, 2, 1, 2, 5. We see those repeat again, right? So what we see is this goes down 3. This one goes down 1. This goes up 1. This goes up 3. This goes up 5. This goes up 7. So it's not a constant rate of change, but the secondary look at that, let me change to a different color for the secondary look here. If we look to see what happens between these with the quadratic, -3 to -1 is +2. -1 to +1 is +2. 1 to 3 is +2. 3 to 5 is +2. So the secondary look at the rate of change, the rate of change is constant. The rate of change, +2, +2, +2, when we look at that. And of course, we can go back to graph that. So 0, 1, -1, 2, 1, 2, -2, 5, 2, 5, 3, 10. So we see our parabola right there. So that's the graph. The vertex, of course, is the lowest point. And so there's some notes for a quadratic, giving us examples of that, graph, a table, and some characteristics. Fabulous. All right, let's look at one other kind. Exponentials. Let's look at exponentials. Exponential equations. So what does the graph for an exponential look like? Oh, there you go. A is the coefficient. B, oh, you're close. It's not B squared. It's B to the X. Right, B to the X. If it was B squared, it'd be a quadratic. Right, so the X is our exponent. In an exponential, our X is the exponent. All right, so an example of that, f of x equals 2 times 3 to the x plus 1. We can have a constant on the end that raises it up on the y-axis. You know, f of x equals -4 times 2 to the x. You know, those are all examples of exponentials. What are the characteristics? What are we looking for in characteristics? How does this compare to the other two that we've already looked at? Has an asymptote? Yes, it has an asymptote. That is correct. It's growth and decay. Yes, so asymptote. Yes. Asymptote. We started absolutely correctly there. We see growth or we see decay. And what does the graph look like for this? When B is greater than 1, it's growth, and below 1, it's decay. That's right. Growth when B is greater than 1, and decay when B is less than 1. Okay. So our graphs for this is straightened and curved. It's almost perfectly straight. It does have a little bit of growth into it. Very, very slow because there's an asymptote that it does not touch. Or we see it coming down the other way. and approaching the asymptote, but never touching it there. So if we want to look at a table example of this, okay, so let's start out with 0.25, and then it goes up to 0.5 and 1 and 2 and 4. Each time it's doubling. See, each time it's doubling. So we see, times 2, times 2, times 2. So what we call it exponential is it goes up exponentially times 2. So in this one, if we graph that at 0, it's at 1, 1, it's 2, 2's at 4, 3 is at 8. And over here, it's just getting smaller and smaller as it approaches. So we see it starting to go up really quick. And over here, it's getting smaller and smaller as it approaches. It approaches y equals 0, but it never gets there. So this one would be exponential growth. It's going up, growth at times 2, as opposed to decay would be going down, and we would have a number it's times a half or something, something smaller than 1. Something smaller than 1 there. All right, very good. Okay. Let's look at some notes here. Well, this has basically the same thing we just did. It just has it all on one page. So you can list an equation example for each one. I'm not going to spend a lot of time on this since we have a lot to go over today. I don't want to take up a lot of time repeating stuff. You can give an equation, what it looks like, an example, a graph. The domain and range is something we didn't talk about necessarily in this. Let's look at that real quick on the last couple of graphs we did. The domain, what is the domain? Domain is all of the x's, correct? Yeah, the x values. And this goes forever this way. And it is going forever to the x's. It's going slowly right, but it's going to go right forever. So the domain on this is going to be every single x, right? All real numbers. What about the range on this, though? So if the domain is the x, the range is the y's. The y's. What is the range for this exponential? What all y's does that cover, that graph? Any thoughts? The range is going to be, well, obviously 1 and 4 and 8 and all these numbers up here included. We have a y for every one of those. All the way down to 0.01 if we keep going. The only y we can't get to is we can't do 0 and we can't do any negative ones. So our range is y greater than 0. Not greater than or equal to. Just all the y's greater than 0 will be included in the range. If it touched the 0, then we could say it's y is greater than or equal to. But in this case, it's just y is greater than. So, all right. So for your example, if you use our graph on the exponential, the range would just be y is greater than 0. If you have a different example that moves it up or down, it's different. Quadratic for this example, it's y is greater than or equal to 1. It actually touches the 1. And the x's, it's going to be all real numbers for the x's on quadratic. So there's a table, talks about the constant change in x, common first difference. The common second difference is what we saw in ours, where we had the quadratic had the 2's as the second difference. And this has a common ratio, times 2, times 2, times 2. All right, all of that. So this page is in the notes, but we won't spend a lot of time filling that out because it's basically a repeat of what we just did. These notes here, you say give the standard form and the basic shapes of each function. So with linear, if we want to give the basic linear shapes, I'm going to change another color just for the fun of it. Mx plus b. If m is greater than 0, what is our graph going to look like? Because it's different when m is greater than 0 compared to when m is less than 0. Right? When m is greater than 0, we've got a positive slope. It's going to be going up as it goes right. But when m is less than 0, I'm going to underline that. When m is less than 0, we've got something that goes downward as it goes right. Something downward as it goes right. Quadratic equations. When a is greater than 0, ax squared plus bx plus c. The a is the coefficient of the x squared, right? The coefficient of the x squared. When a is greater than 0, we have a parabola that goes upward. When that a, or the coefficient of our x squared, and it could all be down here in the negative. The vertex could be positive or negative either way, but it's going to point downwards. And here's that exponential. It's growth when the b is greater than 1. That's when we see it growing as it goes to the right. Where the decay is when it's 0 to 1. It's a fraction. In which case, then we see it generally go downward towards that asymptote. Right, we get into the negative, it kind of changes things around. So when the b is negative, so we're looking at anything bigger than 0. So if it's a fraction less than 1, it's going to be decay. Okay, we won't do many of these. Let's just look at a few of them. Let's classify as linear, quadratic, or exponential growth or decay. Let's start with number 1. What is that? Linear. Yeah, we just have an x in there, 4x, so that's linear. How about number 2? Y equals 5 to the power of x. It's exponential growth. Let's jump beneath it to number 5. Y equals x minus 2 times x plus 7. Yeah, we have an x times an x. We're going to end up with a x squared. And anytime we have the x squared as the largest coefficient, that's quadratic. But right beneath it, y equals 6. Yep. Good job, Ryan. That is linear. There's no x in there. The x coefficient is 0, but it's going to be a straight line. A straight line up at wherever y equals 6. It's going to be horizontal. So horizontal line in that. How about number 10? 10 looks a little tricky. Y divided by x equals x plus 1. Oh, you're quick on that one. That is going to be quadratic because we have to get to y by itself, which means we multiply by x, which means over here we're going to have x times x. And that will be quadratic also. Very good. Let's look at number 7. 1/4 times 3/2 to the x power. I thought we could fool you with the fraction. It is growth because that fraction is larger than 1. Above that, we have decay, right? That's a 1/4, so we'll put decay there just to have a few of those. Looking at these graphs, I think you can do that. That one's pretty simple, right? This is obviously exponential growth. That's obviously linear. That's quadratic, right? So those notes are pretty simple to get because we're pretty good at identifying graphs, right? What about that one? Well, we didn't look at a graph like that. Yeah, that's none of the above. None of the above. That's not quadratic. It's not linear. It's not exponential. It's a totally different graph. It's like an x to the 3rd power graph. So do that one in this row there. Can you identify it off a table? Identifying tables. There's a common first difference of y values for linear, right? Because this is all -1 every time. This one has from -3 to 5 is +8 +4. This one has 0, and this is -4. But what we see here is from 8 to 4 is -4. From 4 to 0 is -4. 0 to -4 is -4. It's that second row, the second differences that are constant. And then this is ×3. Each time we see ×3. All right. And then so we're supposed to label each of these. I will let you guys do that on your own. I can post an answer key on that too. So on these notes, I'll post answer keys. So that way you can double check to make sure you understand it. But trying to get this without taking up 4 hours of class time. So, all right. Good job with that, guys. Like it. All right. That is all of our notes on the first lesson. The first lesson is just about the difference between linear, quadratic, and exponential. So this is the meat of what I want to get in today is linear regression, quadratic regression, exponential regression. Basically, regression is a line of best fit. You may have heard that term for it. Same thing as a line of best fit. So I want to show you, and we'll do that with these examples right here. For each of this, we're supposed to determine, is this linear, is this quadratic, or is this exponential? And then we give a best fitting equation. What equation would best create that right there? So the way we're going to do this is using Desmos. Put this on the screen. And I have a video in Google Classroom on how to do this. So if you don't get this from our class time, there's a specific lesson on how to use Desmos to get this exact information. So we're going to create a table. Up here in the corner, create table. I'm going to use the data that we have on this first table on our notes. We got 0 through 5. And this information is 400, 238, 145, 86, 52, 31. All right, let's look at those points. We have to zoom out a ways because the first one's way up at 400. All right, way up there. Okay. So what kind of graph do you think it's starting to create there? Looking at those points, seeing the data values there, goes from 400 to 238 to 145 to 86 to 52, 31. Exponential. It does look like it started in exponential. I agree, because it's exponentially getting smaller each time. So that means it's going to be an A, B to the X type of thing. So if we want Desmos to figure that out for us, we'll do a Y instead of equals. We're going to use this over on the left side of your keyboard. When you shift up in the corner, there's this symbol, the tilde. This is a tilde. We're going to use that instead of equals. And that tells Desmos, I want you to do a regression line. Figure out the best line that fits my data. And then our equation, of course, be A, B to the X. Oh, it doesn't like that. Why doesn't it like that? Wait a minute. Have I done something wrong from our data? Oh, I'm sorry. We use an X1 and Y1 in this table. So we have to use X1 and Y1 when we tell this to use our data. I just gave it a Y and an X first. And it's like, I don't know what you're talking about. When I use X1 and Y1, now it's going to actually use the data to get a line of best fit. And here is the A. See, 399.5 is the A. And the B is 0.599765. It gives us an A and B to fit into our equation. If we look over here at our data, let's zoom in on these points. That one's pretty much almost right in the middle of it. As we get closer and closer, we can see That is pretty close to that line. I mean, those points aren't exactly on it. If we zoom, see, it's not exactly on that line, but there should be close enough for all 4 points. Let's get way down here. Where's the points down below? I know we got some down here. Get down to 86. So 86. 86 is, it's real close to 86. 86 just a little bit to the left of it. And then we get down to 52. Zoom out. 52 is real close. It's just a little bit to the right. So some of the points are a little bit to the left, some are a little bit to the right, but they all fit really close to that line. So that means our equation would be y equals 399.5. That's our A. And our B would be point. Let's round it to the nearest thousandth, which would be 600, because that 7 is going to round up the 9, and that's going to round up the 9. That's going to be the 600. Parentheses to the x. Notice that line is exactly the same line. I used an equal this time because I typed the exact equation. But that's the exact same line that it gave us. So on our notes at that point, we say, okay, so this is exponential, and it is y equals, what was my numbers again? 399.5. 0.600 to the x. All right, 399.5. So that is the equation that models that data right there. And that's what we do in this right here. Some of our assignment 2 is going to have you doing this. So let's look at another one then. Let's do the second one. Let's go to Desmos. We'll take out this information. All right, just kill all that. Make a new table. And this is going to be 0, 1, 2, 3, 4, 5. And our information this time is 5, 23.5, 41.9, 60.5, 79, and 97.6. So looking at that data, what kind of line does that look like it's representing? Seeing our dots on the screen and our data, this goes up 18.5, that goes up 18.4, that goes up 18.6, that goes 18.5. It's looking pretty linear. Yeah, it's looking pretty linear. So if we tell Desmos we want y equals mx plus b, but we're going to use the y1 and the tilde mx1 plus b. It's okay. We can do that. If you use this m, your slope is 18.5171, and your b is 4.9574. So y equals, and again, we'll round it to the nearest thousandth here, 517. X plus the b is 4.957. That's the exact same line. If we turn the red line on and off, it's exactly the same as the blue line that they figured. Now these R numbers right here for linear R, the closer it is to 1, the more exactly that line will fit. So this one's saying that's pretty exact. If we zoom in on there, those dots are all touching the line. It looks like none of them are off of the line. They're all very, very close to perfectly on the line. So that's our answer. I'm going to write that on our notes. Linear y equals 18.517x plus 4.957. All right. Fabulous. So we would never get these by ourselves without Desmos' help, because getting those fractions would be very, very difficult to calculate by hand. We're not gonna go into this. Can be calculated by hand. We're not going to go into that. We're just going to do it electronically and say we'll be happy with that. Let's look at a quadratic one while we're here. I think number 6 is quadratic. Let's graph that one and take a look at what that looks like when we put it on the Desmos here. So, all right, let's kill that to a new table. This data goes -4, -2, 0, 2, 4, 6. And our Y values are 0, 3.9, 4.1, 0.5, -7, and -18. Oh, -18.3. All right, let's zoom out. Oh, yeah. See, that looks quadratic. It looks like a negative parabola, right? One that's going downward. It's not exponential. It's certainly not linear. So we're going to say, okay, that one looks quadratic. So I'm going to write quadratic on our notes. And let's let this be calculated by a Desmos. So a Y1, using our data, the Y1, use a little tilde. So this will be A x1 squared plus B x1 plus C. All right, give us an equation. There's our A, there's our B, there's our C. And when we zoom in on this, there's the points look really close. This one's really close to being right on there. So they gave us some data that really helps nail our equation because it lands right on these points. That's why it's again saying this is a 1. A lot of times we're going to have points that are off of it on either side, which is fine as long as it's pretty close to a representative of that. So let me write this down. It's going to be a long equation with all these decimals. Equals negative 0.477 x squared minus 0.872 x plus 4.111. There it is, negative 4.77 x squared minus the 0.872 x plus the 4.111. So that is what it looks like using Desmos to calculate the line of best fit or regression line, the line of best fit for all of these. The other page of the notes has the same type of thing. Gives you this information on the left. It says the cost for an above ground pool cover is dependent on the diameter of the pool. The table on the left gives the diameter of 4 different pools and the cost. Using the quadratic model, write a best fit equation. Okay. Then find the cost of a cover of a pool with a diameter of 30. So basically, they want you to get your equation and then extrapolate information from it. After we calculate the equation, we've got to use that to figure out if we were at 30, what would that be? So let's do one of these together. This would be a good one right here. So this, let's graph on Desmos because we're going to need our line of best fit. We need that regression line again. So this is 24, 25, 26, and 27. And the cost is 960, 1,050, 1144, and 1242. All right, this is going to take a bit of zooming out here. Oop, there it is. Okay. It looks very linear, which we would expect as the diameter goes up, the cost goes up because it's so much per foot on there. So let's make this a little linear. Y1 equals mx1 plus b. Oh, but not equals. I got to use the tilde. All right. It says the m is 94 and the b is negative 1298. So let me write our equation on here. Y equals 94x minus 1298. Okay, so that gave us our equation. This is find the cost for a cover for a pool with a diameter of 30 feet. Okay, well this is our x, all right, and this is our y. So if the x is 30, what is the cost? So we say, okay, y equals 94 times 30. We just substitute 30 in for the x, minus 1298. All right, let me bring a calculator up on the screen here. Calculator. All right, so 94 times 30 is 2820 minus 1298. So our cost would be $1,522. $1,522, which looks about right. It's going up over about $100, a little less than $100 each one. So when we add three more, 28, 29, 30, it should be about 1,500. So that looks about right. Using our number sense, we say, if we'd end up with a number like 400, we know that can't be right because these are going up and 30 is bigger. It should be bigger than 1242, but it shouldn't be outrageous like $10,000 or nothing. So, all right, that's the way that works. That's the way that works. All right, oh, that's a duplicate. Same page again. Same page again. All right, with these handout notes, there is extra practice on there. So there's usually the first couple of pages to be notes, and then beyond that, you have pages of practice on there, so you can practice more. It's labeled homework and practice. We'll say homework at the top, but there's just more on there because some people if you don't feel you understand it yet, then there's a few more that you can practice with right there included in those handouts, because I want you to make sure that you have enough practice that you feel good about it. But anyway, I will post. I've got some answer keys for some of those, even for like the homework and practice. So I will post those in our Google Classroom. So if you want to go ahead and work any of the extra homework practice problems, you'll be able to check them right there. But otherwise, I think we've covered everything we have to cover for the week. So you should be able to do both assignments. Like I said, the links are informative. If you don't have a formative account, you may have to create one before it lets you in. Do it with your Google, create with Google. But otherwise, I think you're good. And this week, you only have to be in class if you're below 70. And since we have no grades yet, all of you are above 70. You're still 100%. Everything's had to be turned in. You're 100%. So you don't have to come to class. I will be here. If you have questions, come to class. Don't wait till the end of class. I won't stay here if nobody's here, but come at the early part of class if you have questions. Otherwise, I'll see you next week.
Let's get out of here. Word to your multiples. Math, baby.